right, everyone, let's continue. It's my great pleasure to introduce Johannes Korbmacher, who has been at the MCMP before and now works in Utrecht, has had some substantial contributions to the literature on Truthmaker Semantics, and also edits a comprehensive list of the literature on Truthmaker Semantics, which can be found at truthmakersemantics.github.io. I also posted the web address, into the chat for the online participants. So if you want to check that website out and not familiar with it, it's my pleasure to introduce Johannes. Please, the floor is yours.
Yeah, thanks for having me, even though it's unfortunate circumstances because I'm filling in for Lisa Focus ill and can't make it. So I hope she gets better soon. Consequently, when the organizers asked me if I have something to present, I had something. And then I thought, okay, I cobbled together some slides and I give a presentation on what I'm going to talk about, the grain of Truthmaker propositions. But then I was at this Truthmaker conference and everything was so inspiring that I thought, oh no, I can also prove this and I can prove that. And I started getting results. And I think I have some results. Well, some are computer verified. So that's good. This was one inspiration of this conference. There are some results in here which are a bit more, I call them strong conjectures. I have a proof. I'm just not entirely confident that every step is correct. If you want, we can talk through it. That is, I think, also a more substantial result if it actually holds. There are some results that we have worked through the details and are fairly confident. This is all joint work with Simone Picenni, who's now in Amsterdam. We started working on this when he was in Bristol still, but I have to update the affiliations here. He's in Amsterdam now. We've been working on this for a while. Now there's still development in the project, but it's starting to converge on something. And I hope you find that interesting. So it's the topic, the grain of Truthmaker propositions. It's great to speak at a Truthmaker conference and not have to explain what Truthmaker semantics is. I fit way more material in here than I could under different circumstances. So I can just say, hey, Truthmaker propositions. I'm interested in bilateral Truthmaker propositions. And in their grain in particular, what I mean by that is I should also say that actually, that I'm interested in what's sometimes called the inclusive semantics. So we have closed propositions, closed under fusion, both on the positive and on the negative component. I don't assume convexity, right? That actually a bit more interesting here. Distribution is something we talked about earlier. Actually, in several talks, Kit, you had it as a stumbling block in your talk for something that you don't want to have, and we will not have it, so that's great. So closure, but not convexity. Now grain. By grain, I'm interested in the grain of the propositions. We talk about Truthmaker semantics is more fine-grained than, possible world semantics or maybe intuitionistic logic, than various other semantics, right? The starting point was the question, what does that actually mean, right? How can we make that precise? And also to the extent that we can answer the question, like how much more fine-grained it is. Having a bit more of a grip on comparative grain between semantic frameworks. As you'll see, that leads us to algebra in a moment. But for now, what we can just talk about just propositions on the possible worlds approach. We have here this law of absorption, our everybody's favorite counterexample. So we have that as a propositional identity in possible world semantics. And in Truthmaker semantics, we have at least some settings where it can not an identity. Right? So you have models where the one proposition is different from the other. So here's the one point where I put a diamond over my inequality sign to indicate, well, it's not always different, but it's sometimes different. So in some models, I will be a bit less precise, even not particularly precise, but you will usually know what I mean. I'm trying to not go. So this will become fairly formal, and there's a lot of formulas on the slides, and I try to make it as as little cumbersome as possible. This side condition is important here. So I will, for example, just say they are not identical, but I mean there are models where they're not identical. Well, that gives us here a notion of comparative grain in the sense that, well, here's something that the one semantics identifies and the other distinguishes. Right? But I want to study that from a little bit more general perspective and look at what are now precisely the ones where they differ, right? And at the end of the talk, I will have a proposal for kind of operationalizing this or giving a definition of comparative grain between semantic frameworks. That could hopefully be a fruitful framework for also comparing to other logics. Standard comparison is classical logic or possible world semantics. But yeah, that's the idea. The point here is that we kind of look at it through the lens of propositional inequalities, equalities and inequalities, where we compare those equalities across the different semantic frameworks, and that's kind of the topic of the research. Now we can approach this kind of question from different angles, and the first and kind of maybe standard one is to do this semantically, right? To look at the models and look at the internal structure of the propositions, and then make judgments based on that. Which propositions are equal and which ones aren't, right? So here we get a semantic. If I use this pointer, I don't know if it's a good idea. It's an identity criterion for Truthmaker propositions in a semantic setting, right? They're pairs, so they're identical just in case the two components are the same. And then we can go through the recursive clauses, so conjunction, disjunction, here inclusive semantics, right? You all know this. Then we can look at things and, for example, note that P and P equals P, and we can prove that by like looking at the internal structure of the propositions, right? So we will use the idempotence of the underlying fusion operation, the way that the propositions are constructed from the states to make these kinds of judgments, right? And similarly, to make judgments when something isn't identical, right? So here I'm talking about the canonical model. The counter model, it said at some point in my slides. Now it says canonical model, which is not particularly counter. Still, you know the canonical model, right? Sets of literals are the states, fusion is union, and then you have the standard way of assigning of modeling the propositions there, and then you can find out in that model that, for example, the truth makers of P and P or P and Q are different, right? That's all orthodoxy. The point that I wanted to highlight here is that we were doing this here semantically, right? That works quite well. We can figure out some identities and non-identities. It's not particularly systematic, right? So what we get here is, this holds, this doesn't hold. Is kind of examples. It's anecdotal study of grain, if you will, right? So you'll find some things that are identical here and not there. You list them, but how do you know the list is complete, for example, right? If you want to really seriously compare the grain of the different systems. And the idea is that what we want is some kind of understanding of the laws of propositional identity according to Truthmaker Semantics. We have this kind of understanding actually for possible world semantics. I'll return to that maybe at the end of the slide. But now the question is, how do we get these laws for Truthmaker semantics, right? So that's my aim, figuring that out. And one natural approach one can go is via proof theory, right? Here's a proof system for unilateral exact equivalence, right? So it's a circles here are either conjunction or disjunction, formally disambiguate. But this is a system that where derivability of this equivalence in the system corresponds to sameness of truth makers, right? That's a system that, yeah, I think I cooked this one up ad hoc for the talk. It's derived from a system that is in some paper that I wrote, but we have various ways of building truth maker proof theories. It doesn't really matter. This one works particularly well for what we're going to do, right? You can already see that, well, basically what we want to do is we want to read this equivalence here as identity, right? And this kind of looks like an exhaustive list of identities, but there will be some issues that we'll have to deal with. So we have soundness and completeness for this system in the following sense. That's relatively straightforward to prove. We can prove that the truth makers of the propositions expressed by two formulas, and I'm going to be shifting between formulas and propositions in a semantic way, and here and there it will hopefully usually be clear how to disambiguate what I mean, right? So here, these are these corner brackets are the semantic brackets, right? So we have a language and we have models, and you know what I mean. So we have a soundness and completeness result here for this system that I just outlined, which is a system for sameness of truth makers. Not for sameness of false makers, and that will become important, but let me note this is something that we've also talked about. The way you obtain the soundness and completeness result is ultimately via disjunctive normal forms, right? So you have a disjunctive normal form theorem and you use that, right? Could say maybe a bit more about the models, but I won't. So something to do with canonical models and disjunctive normal forms and being very nicely represented, and then you can very, very straightforwardly give a soundness and completeness proof for this system. Okay. We can get from that system another system which corresponds to propositional identity, right? So same saying, if you will. So two sentences say the same thing in the truth maker sense, express the same proposition, just in case they're both exactly equivalent in the truth maker sense, which I'm going to call the unilateral sense, just to disambiguate from this. Both sides are the same. It's not only the first component which is the same. So both the truth makers are the same as the false makers, but the false makers are the truth makers of the negations. So you can get a system in this way, right? So just take the system that we have, that we know is sound and complete, and that will give us a kind of, in this sense, sound and complete system for propositional identity. So in a sense, we're done, right? So yeah, it's axiomatized, right? It's an axiomatization. Well, sort of, because what this doesn't give us is a kind of direct axiomatization of the identities that hold, right? In this system, we have a bunch of equivalences that are provable, but as we will see, which is also popped up various places in different talks, something being truth maker equivalent doesn't mean it's false maker equivalent, right? So fully equivalent correspondingly. So the question is, can we somehow axiomatize like propositional identity, same saying, directly in the system, right? So that's kind of the question now. The stumbling block is distribution. We talked about that at various points, right? So we have, what am I doing here? Derivation. Should have a counter model, right? There will be a counter model in a second. There is some derivation. Oh yeah, okay. What I mean is like, to try to derive this, and we have, of course, the truth maker equivalence of the two propositions, P or there should be a P and Q or R here, and not a P and P or Q. This was suggestive thinking, because that will play an important role, that formula later. But that should be P and Q or R is P and Q or P and R. And we can derive this as sameness of truth makers, but not as sameness of false makers. So under negation, this is an equivalence, and we know how to get a counter model. Well, I mean, one is going through the details here, but we can find a truth maker of the negation on the one side. It's easy to do this using De Morgan laws. Then it becomes just a negation, a disjunction, conjunction of literals, or things that could be atomic. And then you find a countermodel. So some state that is the truth maker of the one side and not the other. So the two so the negations of these two formulas are different, potentially different, right? As I said, I will speak a bit loosely here. So that's just the failure of the other distributivity law, of course, right? Because under De Morgan, the one distribution law turns into the other, right? They're De Morgan duals of each other, which is also kind of complication that we ran into in this study. Will pop up a couple of times. It's no longer so important as it was in earlier versions of this material. Let's see if I can talk about it at Paris at some point. Okay, so we have that. So we already know that we can't really read the identity, the equivalences in the system that I showed you earlier as identities, right? Because they are not. There are some in there that are not preserved unto negation, which means not for everything in there. It's both. Not for every equivalence that's provable, also the equivalence of the negations is provable. The system doesn't directly axiomatize propositional identity. And that has to do like with the failure of negation replacement. That's basically shown by this, right? That makes the logic that I just gave you thought of proof theoretically a non-congruential logic, right? Which is kind of tricky. That's bad, actually, from a variety of perspectives. I mean, good from a variety of perspectives. So if you want to, for example, as we will do later, look at something like the Lindenbaum-Tarski algebra, where you define, where you have an algebra on equivalence classes of formulas, provably equivalent formulas, and want to define the negation of such a class as the class of the negation, that will no longer be well defined, right, if it's non-congruential. That was one of the first things that got me interested in trying to figure this out, because that means you can't, at least for the system that is there, the unilateral system, really use something like Lindenbaum-Tarski algebra methods, like traditional methods of algebra. So what could we do? Distribution fails, so let's kick it out, right? Does that work? So just take the system from before, take out distribution, we know that that fails. That might give us the equivalences, right? So we can observe already that if we take that system, we do have congruence, so negation becomes congruent, right? So you can go through the individual cases and check, but that's basically just the Morgan duality approach, right? So that could work, right? Unfortunately, it doesn't. Here's an example of something that you can't derive in that system, which, however, holds as a propositional identity in Truthmaker Semantics. Which is a form of closure, right? It's P or Q. That's identical to P or Q or P and Q, right? That's basically directly the clause translated into a propositional identity, right? We can immediately see that holds, but we can't derive it, right? If we don't have distribution. So let me first show you, or try to make it plausible that you need distribution to derive it. Well, you can derive it with distribution. So here's a sketch of such a distribution. Of such a derivation. These are two facts that you need to derive in the original system. So both that the formulas are identical, equivalent, and that their negations are equivalent. And I go through a sketch for the first derivation to avoid all the De Morgan applications and then doing the same thing. And it's anyways a sketch because there are a bunch of steps that you have to, if you look at the calculus very rigorously, it's a very long derivation because substitution isn't really there. It's kind of absorbed in the rules and becomes terrible, but you will get the idea, right? You start with something like reflexivity, and then there's this monotonicity rule that taking on conjunctions on both sides is fine. Disjoining, so taking on disjuncts on both sides of an equivalence is fine. And then you will start applying, there's some reshuffling happening, and then you will start applying distribution a couple of times to distribute things over. Then you have to distribute again. So there's already two uses of distribution here. I don't know, here I'm pulling out, what am I doing? I'm pulling out the conjunction here, I think. So it's better if I do it on the board, but then it will take forever. So what is the distribution that I'm doing here? This distribution is just a distribution like backwards. Well, if I will stare at this formula now forever and not see exactly what I was doing, but you will hopefully believe me that these are applications of distribution that play a role here. Idempotence plays a role, and then we're good. Now, the distribution here is really essential. I have an algebraic argument for why that's the case, which I won't show you the counterexample. That's terrible to look at these algebras. Believe me for now. You will see in a moment how we'll fix that. If you want, we can spend some time drawing like various lattices on the board that will show this. It's not particularly nice. We can use set solvers for this. That might be easier. So you need distribution for this derivation, right? So there is something kind of a role that the distribution plays in the original system to capture full exact equivalence. Right? You can't completely eliminate it. There is something that is still needed. And that is one of the things that occurred to me at this conference when I was, I think it was Andreas' talk yesterday. Yeah, you had this axiom, right, which will now be on the next slide. Here I call it closure. We I don't know really what to call it. It's like this flipping of conjunction and disjunction when there's identical phi or phi and psi is equivalent to phi and phi or psi. There doesn't seem to be a canonical name for it. I asked ChatGPT and it said it holds in lattices. So maybe you want to call it a lattice law. I haven't heard of a good name for it, but actually only that part of distributivity is needed in this derivation. If we have that law, we can get the same derivation. That is a kind of if you look at it, stare at it long enough, you will see that this is basically a form of distributivity with absorption built in, right? That's kind of what happens here. And as we'll see in a moment, actually, this plays an interesting role in capturing closure. Now, this is something that during the previous talk, I admit I was paying attention. I just had to run the proof checker. This law is equivalent to these two laws over the background system. And these are basically absorption laws again, closure laws again, right? It's saying if you fuse a truthmaker of P into the truthmaker T, are they too small? It's P and P or Q is equivalent to P or Q. To add this for P and P or Q is equivalent to P or Q. Q and P or Q is equivalent to P or Q. You could add either those two or this. This is going to be an equivalent system. Right. Against the other rules of the system, you can derive these from that and that from these two. Both are needed. It's a bit like the one that I had there earlier, which had a conjunction here tagged on, right? But actually, that one is itself derivable from these two. Right. Now that looks like a good system now, right? Well, it's a bit trial and error right now. Like, oh, I found a counterexample. Let me fix it and add some axiom to prove it. Now that's complete, right? Well, there's a reasonable suspicion because the thing that was going wrong was to do with distributivity. With closure. We put closure back in. Now we could suspect that this is complete, right? Now we try to prove this, but now we notice a terrible, terrible thing about this system is we don't have distribution, so we don't have disjunctive normal forms. Without distribution, no disjunctive normal forms, and who knows how to prove completeness without disjunctive normal forms? Please raise your hand if you have other ideas. I have an idea here, but look, that's not nice, right? As Truthmaker anecdotes go, that's pretty standard. Right? Okay, so we start doing algebra. The idea is now that taking a real algebraic perspective will allow us to get a better grip on this, right? And we'll try a couple of things. It turns out that both systems play a role, both the kind of unilateral equivalence, the positive equivalence systems, and the full equivalent systems, equivalence system. But the idea that we now use is to like forget about the internal structure of the propositions, no longer work semantically. You could say that the proof theoretic approach is also ultimately semantic, right? We're using soundness and completeness as the guide here, right? We're not really looking at the algebras where we're going, like we were still kind of tied to the semantic underlying structure, and we try to get it as far away from us as possible, even though Truthmakers, I like semantics, but for this purpose, it would be good to get it, to forget about it for as long as possible and then reintroduce it only at the very end back into what we're doing. So we will now just have propositional algebras, which are, just a carrier set with operations. Here we'll just use the same symbols as, so I could just either write times, plus, and minus or something here. But I think it's more transparent if I write it like this. And then valuations become homomorphisms, which is basically maps that preserve the operation. So we go from our language into these algebras, and that's how we interpret them. Right? It's directly an algebra of propositions that we're now looking at. Right? And we're going to take these as the objects of our study, and we'll try to figure out what are the algebras that correspond to Truthmaker semantics. And we will do that mediated by what we know is a sound and complete proof system, right? So that will be the guide, and then the semantics is start looking at what does that tell us about the propositions if we analyze it algebraically. That's the project. And now the first thing I actually already said that. So here's how we build the Lindenbaum-Tarski algebra, right? So you probably know this already, but you take the equivalence classes of formulas to be the elements of the carrier set, so the propositions, and then you define kind of in the stupidest way possible the operations. Just the conjunction, algebraically speaking, of two propositions is the equivalence class. So propositions of two equivalence classes is the equivalence class of the conjunction, disjunction, negation. Right. Now we already know that doesn't work if we have only the positive system. Right. This is just not well defined, the last operation here. Do I have a bullet point on this? Yes. So now I will use a B for like bilateral or full system, and the U for the unilateral or positive system. So this is well defined for the one and not the other. Right. For the other, we have soundness and completeness. There we can't apply it. For the one, we don't have soundness and completeness. So what does it help us? Right. Well, we continue thinking a little bit, and some things will emerge. So the first thing is that there is a sense in which you have if you just take that algebra as a single class, the only model that's allowed, right? You have a kind of trivial soundness and completeness result, right? So that system, that algebra will distinguish all non-equivalent, non-provably equivalent formulas because they're built to be identical if they're provably equivalent, right? So there is this is under the kind of trivial homomorphism where you map the atoms into their equivalence classes. So this is all stuff that you use standardly in algebraic logic. One thing that you always, when you start doing algebraic logic and you have Lindenbaum-Tarski algebras, you notice that if you have a class of algebras over which your system is sound, right? meaning in our case that provable equivalence means identical under all homomorphisms. And that class contains the Lindenbaum-Tarski algebra. Then you get completeness for free. Right? So soundness is something it's not super difficult to prove in these classes, and completeness will just be showing that the Lindenbaum-Tarski algebra is in there. Actually, I'm going to do some kind of proof like this as a completeness proof for the conjecture of theorem, soundness and completeness conjecture, which I have a proof for, but we talked about showers and such ideas. I had this idea falling asleep, and it was there when I was in the morning, and it worked. I think I checked the cases, but let's try to look at that a little bit more and try to see if we can obtain some sharper results. To see that what we somehow want to do is we want to have, basically, we want the class of propositions over Truthmaker models to be, so we want our logic to be sound for that, and we want the Lindenbaum-Tarski algebra to live in there, right? So that you can get the Lindenbaum-Tarski algebra of that logic as a logic, as an algebra of propositions, or isomorphic to an algebra of propositions over some state space. There I have an idea how to do that, but well, a sec. Patience. Basically, the kind of structure that we get from this B system, right? It's a bilateral or full system, is what's called a De Morgan bisemilattice. The last one at the closer. This is a De Morgan bisemilattice. Again, uniformly disambiguate the conjunction and the circle as conjunction or disjunction, right? You have 6 idempotence community and associated laws. And you have double negation identity and De Morgan laws. These are studied and well-known algebras, right? So bisemilattices, some Polish logicians that, well, actually also, they're all Polish. So Romanowska is published a lot on bisemilattices with or without distributivity. And then there's this guy, I think, one of those Polish names with a lot of consonants, and I think it's Brzozowski. Correct me if I'm wrong. So Brzozowski had the De Morgan bisemilattices, right? So these are known structures. So that was also kind of nice, right? So that what we came up here is like, this is something, if you read the equivalences in the bilateral system as identities, that's what you get, right? Well, you have to add this kind of closure thing, or toggle, or I call it closure now because it somehow captures the closure. That's the kind of algebra. And if we take these algebras, then you can notice some things, right? So all the algebras of propositions over state spaces, they will be De Morgan bisemilattices with closure. I think DMBC, I call them from now on. So there will be DMBCs. We can also can get the last Lindenbaum-Tarski algebra, very easy to show that it's a DMBC. So with respect to the class of DMBCs, the Morgan bisemilattices with this closure thing, we get an algebraic completeness result. Again, kind of trivial because the Lindenbaum-Tarski algebra is in there, and it's super easy to see that this is sound. Right? Basically, just build in here. This is the kind of algebraic result where you're wondering what's the point, but we will get to some of the points later, right? So it's you have an algebra, it's complete with respect to these algebras. Now you want to see if these algebras somehow arise in interesting ways, right? So we have an algebraic completeness result. That's not really what we're after as Truthmaker Semantics, because we still care about the truth makers. Right? So we will carry on. So the kind of open question is whether the Lindenbaum-Tarski algebra is isomorphic to some De Morgan bisemilattice with closure over a state space. I do have a construction. We'll see. If we have time, maybe later, I will show you the construction. It's not very hard. I will show you a construction that's very similar to it. And I need to realize that we can do the same construction to get a state space. And then you will maybe believe me a bit more that we have this result. Okay. So what we did then is we pushed on and thought, okay, can we find some other ways of narrowing things down so that we get an interesting class of algebras associated with the logic that we can somehow represent nicely, make clear that it's a truth-maker proposition related to state spaces. And for that, we looked into it's called abstract algebraic logic, which has somewhat more generalized notions of models around than what we've been talking about so far. These are interesting because they find, as you will see, I will explain now how they work, but kind of for the idea, what we do is we try to associate with a logic, in our case, exact equivalence, a class of algebras that kind of captures the information, the equivalential or identity information about propositions that are contained in the logic. Right? If you want to read equivalence in the logic as identity of propositions, which is what we don't do with the one that we're interested in. And that's actually specifically what they're after. So we try to see, okay, let's try to figure that out, right, and see what we can get from here. So don't want to go through the entire history of how these models came about, but they're kind of a generalization of a generalization. They are, however, a fairly simple idea, right? So you really take a model now, kind of sort of in the first order sense, right? So you take an algebra as your object, and then you have a consequence relation on it, kind of arbitrarily. So it's just a Tarski consequence relation on the propositions in your algebra. Doesn't need to satisfy any laws yet, right? You call it a model if, well, it does respect your logic under all homomorphisms. So that's a very general definition of a model, right? It's to me, it feels a bit like a first order model, right? Where you're not putting really, so there's not nothing built in about interesting ways in which the propositions interact or truth or anything like that, right? Basically take you think, oh, consequence relation over the propositions, one that behaves like the logic tells me it should, right? That is a very generalized notion of a model, and there are many models like that, some stupid ones, right? So like if your propositions are there's just one and it implies itself because it's the Tarski consequence relation, that's going to be a model of our logic, right? So models are just sound, right? Completeness will get. So that's a kind of in a sense, it's a stupid notion of a model from a traditional perspective. But as we'll see, this notion of a model will allow us to kind of narrow down the class of algebras that we're interested in. So what we kind of want to do is which one are the correct models, and we will look at those where the consequence relation interacts with identity on the propositions in an interesting way, such that it kind of absorbs the information about identity that the logic has. And that's what we'll look at. I'll run you through the definitions now. You don't need to worry about the details too much. There is a bottom line at each of the next two slides where I try to go a little bit more into the details. But the bottom line is actually enough, I think, to understand what's going on. So we'll now look at certain kinds of models. Right? So first one we look at are what's called reduced models. Reduced models, to understand what that is, we need to talk about congruences. Congruences are basically relations that preserve the operations. Right? Non-congruential logic. Congruence is something that respects the operations. Right? So we'll be dealing with congruences, well, not yet. This isn't a congruence yet necessarily. The Frege relation, sort of swap this around. The Frege relation on a model is the relation that holds between two propositions in the model, and we're talking about models here, right? So the ones that behave correctly. The Frege relation is the one that holds between two propositions just in case they have the same consequences according to the logic. Here now is the first time that I really have consequence. So far we had equivalence, but we can go back and forth, right? And just define right. There are different ways you can spell this out, but you have the kind of the idea of having the same consequences. So that's the Frege relation that can hold between two propositions in a model. And now we have another notion, and then we'll get to the point. The other notion is what's called the Tarski congruence. And the Tarski congruence is the largest congruence with respect to inclusion below the Frege relation. So the Frege relation doesn't need to be a congruence. Right? We've seen how that can fail, right? But what we want is we want to look at the kind of the largest congruence with respect to it, right? Below it, that kind of approximates it, right? And we want that to be identity. That's a reduced model. Which is a sense in which we try to identify as many propositions as possible, right, to get kind of the right kind of grain in a model. So we want to have identities, if we can, between two things with the same consequences. If we can't, we don't, right? And we do this in a congruential way. That's a reduced model. So these are already much better models, right, that tell us more about the propositional identities in these models. That's not enough. We also have full models. So as you can see, this is about the identity of the propositions. Right? The notion of a full model has to do with the adequacy of the consequence relation, because also there, you can have models with very stupid consequence relations or equivalence relations, right? Where just everything is equivalent. They're going to be models, right? But they're not very interesting models, right? We want to have better models where the consequence equivalence relation approximates the actual relation that we're interested in more, right? And the way you do that is that you have, kind of minimal models. So you have an inclusion relation among models where you models with the same propositions in them, right? And then you take the ones that have where the propositions have few consequences as possible, while still being a model. The minimal models. Full models are then lambda, so that's Frege relation quotients. So you identify then again propositions, and you get something which is a notion where you don't have too many consequences, right? You try to have you have the grain and you have the consequences, and you want these to play together well, and then you get a full reduced model. Right? And a proposal for the algebraic counterpart of a model that is around and established in abstract algebraic logic is that of a full reduced model. Right? The class of algebra reducts, as you would say if you do algebra, is that so the underlying algebras, propositional algebras of all full reduced models, that class. That gives very good results in known logics. Right. For classical logic, it gives you Boolean algebras. For FTE, it gives you De Morgan lattices. For intuitionistic logic, it gives you Heiting algebras. It really gives the right results, right? It also feels feels good, right? We have this motivation for why it works the way it does. Now, we try to characterize that class initially for the unilateral, the positive equivalence system, but then also for the fully equivalential system. Right? And that's a conjecture still, but I think also that is a strong conjecture. I have, again, a proof written down, not really checked with some distance between. And so I write it as a conjecture, but for the bilateral systems, this just should be the De Morgan bisemalatices with the closure property. Right? So that gives us maybe already a bit more comfortable now with the De Morgan biassembly lattice with DMBCs. It's a much weaker conjecture, but I'm starting to get a bit more convinced of it, that actually this coincides with the algebraic counterpart of the unilateral system. A bit weaker, but I noticed some proof theoretic facts about probably two systems are equivalent, that should be equivalent to get this result. Here, I don't have a proof yet. I have an idea of a proof, but yeah, that's why it's a weak conjecture, right? Like a true conjecture. Yeah. So we do have some results about the algebras of the unilateral case, and they're kind of interesting. And they will also, and then I'm done. They will, no, I'm not done. I should say something else. But I'll run you through these results real quick, because there's a construction in there. It's kind of interesting, and that will actually, that is actually the construction that placed most of the work in the previous conjecture, where do have the proof that we can build the Lindenbaum-Tarski algebra of the bilateral system of full exact equivalence from a state space. Right. That works very similarly to what we did here to get some representation theorem for the algebra of the unilateral system. So let me just show you what we did. So we start with a kind of different structure, right? Which is something that you would kind of expect to have, which is a biassembly lattice with just one distributive law. That's actually the title of one of Romanovska's papers. So these are interesting structures, right? If you have De Morgan laws as well, right, you can't really have those. Then you have either both or none, right? Because the De Morgan dual, right? But when you don't have negation yet, you can have them. Right? We start with those. This is kind of an algebra of the positive contents, if you will. Right? And what we did is we take one of those guys and flip the operations around, and then build kind of a product algebra, which is pairs of propositions from the original space, right? Which, because the flipping around doesn't really do anything. So basically, yeah, absorbed here. We take now pairs of these propositions, and then we define the operations using the original operations in the truthmaker-y way, right? And negation becomes flipping, right? It's a way to take the cases where we have distributivity and build off those things where we don't have distributivity, not necessarily, right? But we have something like a truthmaker algebra. Right. And the point here, that's the theorem. I really have to say, like, Simonas, for his PhD, proved a lot of this. So I just had some ideas here for the proof. It turned out to be 50 pages, but a lot needed to be checked, but it works out. So in the class of algebras that correspond to the unilateral system, right? One with distributivity, which, you know, every algebra in there can be represented as one of those guys here that are constructed, and vice versa. All of them in there are constructible in that way. So that class can really be represented in this way. That was the first result that we obtained. That gives us a characterization of the class of associated algebras. You know, we could start proving more things. We tried, because we hadn't figured some further things out yet. We tried to figure out, okay, so there's this notion of a variety, a class of algebras that can be defined equationally, right? That's what we're after. And there are results for proving that a class of algebras is a variety. And once we have a bit more of a grasp on what the class of algebras looks like, we could start trying to apply those theorems. It's a Birkhoff theorem that has some conditions, preservation. So products have to be, there has to be closed under products, that class, There are some preservation properties that we couldn't figure out. We went to a weaker thing, and that we could check. It is at least a quasi-variety that we have a proof of. A quasi-variety is kind of like a variety, except that you can have conditionals in the defining. So if this is identical, then that is identical. Right? Not only just, oh, these guys are identical. That's a quasi-variety. We know that it's a quasi-variety. It could very well still be a variety. In fact, we think that we now know that it is a variety. Know is strong. I now believe more than disbelieve, even a bit more than disbelieve, that this actually is just DMBC again. Because the DMBCs can be constructed in the same way, and it all works out nicely. Yeah, that's the conjecture here. Again, there are some. There are more steps missing, or there are no steps missing. They're just not really thought through again with a clear mind. Not after like 3 days of Truthmaker. Okay, so that's what we got. Let me now return to the initial question of grain. So these are the kind of results that we have, right, and conjectures. Again, we can talk about this completeness proof. I think that would be actually something that is maybe fruitful also. So being able to construct these DMBCs, the Lindenbaum-Tarski algebra as from a state space. Then we have a completeness result for that logic. So then it will be sound and complete for propositional identity over a propositional identity of propositions over state spaces, Truthmaker propositions. I'm now going to assume that for a moment and continue on that assumption, because with that, if that's really true, which I think it is, the things that I want to talk about to wrap things up are a bit neater, cleaner, easier to explain. Right? I have to do with grain. So let's assume that is all true. If you want, we can talk about the proof. So what I want to now look at is, so we have this class of DMBCs there. This is essentially the class of Truthmaker propositions, Truthmaker propositional algebras. Now you have this notion of a free algebra. Right? A free algebra is one which, when it's generated by some elements, then every other, so that's relative to a class, then if your algebra is generated from some elements, then whenever you map these elements into some other algebra in that class, and basically all you're doing is identifying element from your original algebra via homomorphisms. Homomorphisms are basically identifications that respect the operations. So the Lindenbaum-Tarski algebra, which is generated by the equivalence classes of the atoms, right? What generated just means, well, you can get any element by just applying the operations consecutively and then get every element, right? That's free in this sense, right? It's basically the term algebra, which is just this kind of trivial syntactic algebra that you can build by just building up the terms and looking at that as an algebra, factored by the laws of De Morgan bisimilarities, right? So identify things that De Morgan bisimilarities tell you to identify. It already goes in the direction of what I want to say. It's kind of the most fine-grained De Morgan bisimilarities with this law, right? So it's the most fine-grained Truthmaker proposition algebra. So the proposal that I want to make is take that to be the granularity of Truthmaker semantics. The algebra itself. We can identify concepts with objects. Granularity is this algebra. When we do that, if we do that, we can have this notion of comparable grain for two different logics. We can play the whole game for another logic, get its most fine-grained algebra, and compare it with our most fine-grained algebra. And then we have a notion of one logic being more fine-grained than another, on semantics, if you look at the logic coming from the semantics, just in case, well, there's a surjective homomorphism from the Lindenbaum-Tarski algebra of the one to the other. think about it so if you don't believe it now, think about it for a second. It's not very hard to see, because if you preserve the operations and you have the same vocabulary, then really all that can happen in homomorphism is to identify things, right? And if you do that in a surjective way, then you have fewer propositions before than when you started, right? You don't have more over there, and that means the one is more fine-grained than the other. And now it can happen that two logics are incomparably grained, right? So it could just not be such a homomorphism, right? So you have something like a partial order on logics with respect to grain, which gives rise to this nice structure. It's what the mathematician likes. And so first proposal for comparative grain. Here we can now show Truthmaker semantics is more fine-grained than classical logic in the following sense. These are the identities, these are the identities, these can be mapped over there. That's it, right? We can compare it to other frameworks if we play the whole game for these other frameworks and say, hey, maybe it's incomparably grained, or maybe it's more fine-grained, or it's less fine-grained, right? If you do like Impossible World semantics in all its glory, you got something super fine-grained, right? Which you can, it's basically syntax at that point, right? From an algebraic perspective, it just is syntax. You get that to be more fine-grained than Truthmaker semantics, right? You can get all these kinds of interesting results. So that kind of puts Truthmaker semantics on the map somewhere, like of comparative grain, right? And then the question is, where's the right level of grain? We can ask all these kinds of questions. That's not what I'm doing today. I was trying to communicate some results, some hopeful results. And oh yeah, there is this point about different vocabulary here. This is for logics of the same vocabulary. There were some suggestions. Simone talked about this at some point. We're thinking of considering what happens when you have different vocabulary in the logics, like one with modal operators, the other without, or something like this. What can you say about grain then, right? You can think about interpretations. Oh yeah, I have to. It's not full screen, maybe. Interpretations between the languages. So like maybe you can. But this is the kind of stuff that Jan van Bentham had his note on Truthmaker semantics and modal logics, right? That's a kind of interpretation. You could still potentially compare the grain of the two frameworks, right? Well, there's lots to be done. I think we have some interesting results, some hopefully I find great results, because it's a completeness proof without disjunctive normal forms. Well, not really. They're hidden in there. And if you ask me about the details, I will tell you how they're hidden in there. You actually need to combine both logics in an interesting way to construct that state space. So there's still, after all, but it's an idea for how to do, in principle, completeness proofs without disjunctive normal forms. I think I'm going to stop here and say thanks to you and the organizers.